this video, we will discuss a brief introduction of the Laplace transform and its application to the study of continuous time systems, or the transfer function. The Laplace equation and the Laplace transform was discovered by Pierre Simon Laplace, a French astronomer and mathematician. Laplace became a professor of mathematics at the age of 20 and believes that the universe is nothing but a giant problem in calculus. The Laplace transform is a frequency domain representation that makes analysis and design of linear systems simpler. The Laplace transform is a well-established tool in analyzing continuous time linear systems. It is important for a number of reasons. First, it is applicable to a wider variety of inputs. The Laplace transform of an unbounded signal can be found. Second, the Laplace transform is powerful for providing us in one single operation the complete response, that is, the steady state plus transient or homogeneous and particular. Third, it automatically includes the initial conditions in the system analysis. It allows us to convert ordinary differential equations into algebraic equations, which are easier to manipulate and solve. It converts convolution into a simple multiplication. Fourth, we can apply Laplace transform to generate the transfer function representation of a continuous time LTI system. Now, we can begin the application of the Laplace transform to the study of continuous time systems. The output y of t can be represented as the convolution of the input x of t and the impulse response h of t. By applying the convolution property, we can obtain y of s is equal to x of s times h of s, where h of s is equal to the ratio of output response y of s and input x of s. This representation of h of s is known as the transfer function or system function of the system. The transfer function of a system describes how the output behaves with respect to the input. In this figure, the relationship between the impulse response h of t and the transfer function h of s is shown. You can see that the output response y of t is equal to x of t convolved with h of t, and y of s is equal to x of s multiplied to h of s. A linear system is often specified in terms of a block diagram. Here, we can consider three types of interconnections. First, a parallel interconnection of two systems. Transfer functions h1 of s and h2 of s with a single input x of s and single output y of s as shown in the figure can be represented as y of s, which is equal to the sum of the two transfer functions multiplied to input x of s, or h of s, where h of s is the overall transfer function of h1 of s and h2 of s. Second, we can consider a series interconnection or a cascaded connection of two systems, which is represented through this figure. We can derive y of s, which is equal to h1 of s times h2 of s times x of s, or h of s, where h of s is the transfer function of the overall system. Finally, we consider the feedback configuration. In this case, the output is feedback to the input. Negative feedback is common in practice because positive feedback can cause system instability. Considering the feedback configuration, we can say that y of s is equal to g of s times u of s, but u of s is equal to x of s minus f of s times y of s. Substituting u of s to y of s will result to this equation. Dividing both sides by x of s, we can obtain h of s, which is equal to g of s all over 1 plus f of s times g of s. Now, we can try to solve problems using the concepts of transfer function. For our first problem, with the given input x of t equals u of t and an output response y of t equals sine 3t, find the transfer function h of t of the system.
So for our example, we have the given x of t equals u of t and y of t equals sine 3t u of t. So we also know that h of s is equal to y of s over x of s. But in this case, we don't have both. But we do have x of t and y of t. So we're going to take the Laplace of those two. So the Laplace of x of t equals u of t is equivalent to x of s, which is 1 over s. Then the Laplace of y of t, which is sine 3t, so which is equivalent to y of s and equal to 3 over s squared plus 9. So now that we have both values x of s and y of s, we can substitute those two to the transfer function equation. So 3 over s squared plus 9 over 1 over s. We perform algebra. Yeah. So we're gonna have 3s over s squared plus 9, which is the transfer function. But in the problem, h of t is being asked. So we're gonna have to perform inverse Laplace transform in the transfer function h of s. So 3s over s squared plus 9 inverse Laplace will be equal to h of t. Okay, wait. Sorry. Okay, here. H of t will be equal to 3. So s over s squared plus 9 is equivalent to cos. So it's gonna be 3 cos 3t u of t. So that's gonna be our final answer for the transfer function.
For our second problem, we can refer to the figure shown. A system is characterized by the transfer function g of t equals 2s plus 3 all over quantity of s plus 1 multiplied by the quantity s plus 6. Find out how the system responds to exponentially decaying output r of t equals e raised to negative 2t. Find the transfer function h of t of the system.
Okay, so for the equation before, we have the given g of s equals 2s plus 3 all over the quantity of s plus 1 multiplied by the quantity of s plus 6. We have another given, which is r of t equal to e raised to negative 2t. So we have the formula for the output response c of s, which is equal to r of s times g of s. So we have r g of s but not r of s, but we do have r of t. So we're gonna have to perform the Laplace transform for r of t, and we can obtain r of s, which is equal to 1 over s plus 2. So now we can substitute r of s and g of s to the equation c of s. So c of s will be equal to 1 over s plus 2 multiplied by 2s plus 3 all over s plus 1 times s plus 6. Okay, so we can write this equation into the form of 2s plus 3 multiplied to 1 over s plus 2 times s plus 1 times s plus 6. So we're gonna have to use this formula later. So this is equal to c of s. Okay. So we have 2s plus 3 all over quantity of s plus 1 times quantity of s plus 2 times quantity of s plus 6. It can be written in the form of a all over s plus 1 plus b over s plus 2 plus c over s plus 6. Okay, so we're gonna have to find a, b, and c. So for a, we have 2s plus 3 all over s plus 2 times s plus 6, where s is equal to negative 1. So if we solve this, we're gonna have a will be equal to 0.2. And then b, we're gonna repeat the process, 2s plus 3 over s plus 1 times s plus 6, where s will be equal to negative 2. So b will be equal to 0.25. Okay, so next is c. This will be the last. So 2s plus 3 over quantity of s plus 1 times quantity of s plus 2. So where s will be equal to negative 6. So we will obtain c equals negative 0.45. So we will use these three values later. Okay, so the values before a is equal to 0.2, b equal to 0.25, and c equal to negative 0.45. We will substitute this to our equation. So c of s equals 0.2 over s plus 1 plus 0.25 over s plus 2 plus negative 0.45, so we can change it later, over s plus 6. So to be able to get the transfer function, we're going to have to perform inverse Laplace transform for c of s. So c of t will be equal to 0.2 times e raised to negative t plus 0.25 times e raised to negative 2t minus 0.45 e raised to negative 6t. So times c of t. So this will be our final answer for the second problem.
So that sums up our discussion for the Laplace transform transfer function. Thank you for watching!